Hello, everybody. Welcome to my Physics 2 Lab 4 report on bar magnets. The code is on the top left of the screen. So, the purpose of the lab today will be to measure the distance dependence of the magnetic field due to a small bar magnet and compare your measurements to the distance dependence predicted by the equations for the on and off axis magnetic fields derived from the Biot-Savart law. A real magnetic compass, of course, is a good detector of magnetic fields, but the compass app on your smartphone is actually rather bad at this task. So during this experiment, the compass apps often use GPS tracking to calculate true geographic north, so we shouldn't use that in our experiment, and sometimes use advanced signal processing to filter out local magnetic fields. We need to use a dedicated magnometer app, not the compass app, to measure the magnetic field due to a permanent dipole magnet. This way, it's accurate data, or at least as accurate as it can be, without the change from a GPS. So some fundamental physics principles now here include the magnetic field equation. B equals U naught over 4 pi times 1 over R cubed times 3 dotted U R dotted R minus U. We also have B bar equals K R to the N, which will be used later to figure out magnetic moment. Same with ln of Bx equals ln of K plus N ln of R. It's just the ln of the equation above. We also need to know magnetic moment, the thing we want to solve for, what magnometers are, the thing we're using to measure, and our systems and surroundings, the system being the bar magnet and its magnetic fields, while the surrounding being everything else, like external magnetic fields, unrelated to the bar magnet. So for this lab, we need to remember to compensate for magnetic moment, as I said before, by aligning our meter stick with east-west, same with our phone. So we're adjusting for north. We're not including it. And the predicted value for north is relatively the same as what we got from the magnometer. So we can relatively say that latitude 33.749 and longitude 84.388 is pretty accurate for 49 UT. And then finding our magnometer chip, we also need to do so we make sure our measurements are accurate. We just need to follow a procedure by going down and up the ruler, looking at different values, and putting tape on the ruler to mark the spot on the phone. So our measurements and our results we got include this graph that resulted in K being 1.121 UT over A times meters squared, N being negative 2.2432 meters, and U being 5.6 amps per meter squared. And here are the table of measurements we did for our off-axis fields, averages we got. Just minus this. And then what do these statements describe what we saw? Well, of course, in 1 and 4, the magnometer measures around 0 when it's far away in the x direction, but as you get closer, the measurements increase. So here's the code we got. This is just showing the magnetic field of course, the magnet itself. And we have values we calculate, including the magnetic field at 45-degree distance, which is relatively similar to what we got in experiment. And there's the code for initial values and magnetic field calculation. We have code for showing the vectors, scaling them, code for calculating the vectors, more code for calculating the vectors again. And lastly, the code used to calculate d perp and for r 45 degrees, magnetic field 45 degrees, etc., and drawing those vectors. So what if you have oriented your experiment to compensate for magnetic north? What if you hadn't done that? Well, without compensating for magnetic north, the results would vary in accuracy. In the x component, values of n and k due to the interface of the Earth's magnetic field would change completely. The results would be even greater, would be that there's an even greater difference in experimental to computational values. Furthermore, what if we were to stick two identical magnets together end to end and run the experiment? Well, if we did that, if we put two identical magnets together end to end and ran the experiment, the results of the measurements would double. Furthermore, they wouldn't change directions, they would just increase in magnitude. And for sources of error, there may have been some external magnetic fields from the electronics messing with the measurements, and an inaccurate ruler measurements, of course, because those rulers were not at all clean. Thank you.